Hello everybody, welcome back to another video. We've got Leo and
Eric.
ready to do question 2 of Thermochemistry 2023.
Yes, bro.
I hope you're excited because this one's a doozy.
Because Leo's gonna cook it up.
Here we're asked to write the equation that has an enthalpy change equal to the first ionization energy for the element gallium.
GA.
So the first ionization energy is when a gaseous molecule loses one gaseous molecule is one electron to become an ion.
That's right, Leo.
So, got gallium as a gas goes to Ga plus an electron.
That's outstanding work. Good
Thank you.
job.
So we are asked to use our knowledge of periodic trends to identify and justify the differences in the first ionization energy of gallium and selenium. We're going to pass this on to Eric for some more insights and fun facts.
Oh, alright. So, let's justify the difference in the first ionization energy between gallium and selenium. First, it's good to look at our periodic tables for trends, since that's really what the question is asking us to do. So, selenium is here in group 16, whereas gallium is in group 13. GA has 4p shell, 4p1, and SE has a 4p4. Very nice picture, outstanding, Leo.
Thank you.
GA has a 4p1 shell, whereas SE has 4p4. So therefore, GA has is easier to lose one electron than selenium, because it only has one lonely electron in its outer energy level. So to answer this question, I think it's good to be a bit straightforward to just state out which one has a greater first ionization energy than Ga. So since Ga, it's easier for gallium to lose an electron, therefore selenium must have a greater first ionization energy than Ga. So let's write that down. Ionization energy than Ga. So although the valence electrons are in the same energy level with the same repulsion as shielding from inner shells, the number of protons increases across a period. So what this is saying is that since it's in the same groups and periods, since it's in the same period, you'll have the valence electrons are in the same energy level, so you have equal amounts or strength of electron shielding from inner shells, but the number of protons increases across a period. So for selenium, it is further to the right, so it has more protons in the nucleus. Therefore, it has greater pull, electrostatic attraction on the valence electrons. Therefore, for selenium, more energy is required to remove the outermost electron, and hence Se has a greater first ionization energy than Ga.
Lovely explanation, Eric.
So Leo, would you like to do part 3 of this?
Sure, Eric.
Let's go, Leo.
So, use your knowledge of periodic trends to explain why gallium, Ga, has a larger atomic radius than boron, B. So, looking at our periodic table here, we've got boron and gallium. Now these two are in the same group. Here's boron and here's gallium. So because they're in the same group, they will have the okay, so going down a group, we go down an energy level. So we'll have another energy level added, another one. So the valence electrons will be added to an energy level which is further from the nucleus, since this has more energy levels. So this means that gallium will have increased shielding than boron because it's further away and has more energy levels.
That's indeed correct. All right, Leo. So but the number of protons increases as you go down. So wait.
Well,
so shouldn't boron have a bigger radius than gallium?
Well, even if that is the case, this attraction is offset by the increasing distance between the nucleus and valence electrons. So the electrostatic attraction between the positive nucleus and its valence electrons decreases, and therefore the atomic radius of gallium is larger than the atomic radius of boron.
Ah, that's so insightful, Leo.
Yeah.
Right.
Yeah.
So, should we move on to B part I?
Okay. All right, Eric. So we've got the reaction of ammonia with carbon dioxide to produce urea, CONH2 So we need to calculate the standard enthalpy of formation of urea, which is this. So the formation of urea is going to be Let's get Eric to write this one. Wait.
That's all right, Leo. So we'll look at this question. The enthalpy for reaction is negative 89 kilojoules per mole, and this equals to the enthalpy of formation for the products minus the reactants, if you remember from year 12. So we asked for the standard enthalpy of formation of urea, so let's make that x. So we have x plus the enthalpy of formation for water, which is negative 242. And then we have, so this is the sum of formation for the products. I have to take away the sum of the enthalpy of formation for the reactants. And this would be 2 times the NH3, which is 2 times negative 46, plus the formation of CO2, which is negative 394. And let's do some math here. So this simplifies down to x plus
244.
That's indeed correct, Leo.
Yeah.
My trusty calculator.
That's equal to negative 89.
Yeah, that's equal to negative 89. Let's do some year 9 rearranging. We have x equals negative 89 minus 244, which is...
Yeah. Negative 333.
And what's the unit, Leo?
That would be in kilojoules per mole.
Ah, very nice. And there is your mirror mark. Very nice.
Mm.
Would you like to do part 2, Leo?
Well, we'll see. So we need to explain what would happen to the delta RH provided in part 1. That's this. Wait. If the water was produced as a liquid. So here, the water is produced as a gas, but we need to figure out what would happen if it was produced as a liquid. So, if liquid water was produced instead of gaseous, there would be heat energy released as intermolecular bonds form between the liquid water molecules. That means, as a result, the enthalpy change will be more negative. Let's pass it over to Eric for more insight on the situation.
Very nice, Leo. I think you've covered most of it. You're right that if liquid water is produced instead of gas water, then heat energy will be released because intermolecular bonds form between liquid molecules. So you'll be more exothermic because it's bendo and mixer. So it's making bonds. So there are more bonds or making bonds for liquid water than gas. So it will be more exothermic. If it's more exothermic, then the enthalpy change overall would also be more negative. So will be more negative. More negative. Very nice. Right, and this is question 2.
Yay!